I'm doing my video over chapter 10, the structure and synthesis of alcohols, and first let's look at the different types of alcohols. Down here I've written the basic structure of an alcohol group, and as you see it's just any carbon chain, carbon connected to an OH group. So these are the 5 different types of alcohols you'll primarily see. So the first one is a primary alcohol, where you have the OH directly connected to a primary carbon, and then a secondary alcohol where you have the OH directly connected to a secondary carbon. A tertiary is where the OH is connected to a tertiary carbon. This phenol group is where the OH is directly connected to a benzene ring, and it can be anywhere on the ring, it's just connected to it. And a vinyl alcohol is where the OH is connected to a carbon that has resonance with a double bonded carbon. But once again, the basic structure of all of these is an OH connected to just a carbon chain or like a benzene ring or something like that. So next we'll look at naming, how to name an alcohol. Alcohols have a suffix of OL at the end of a chain. So for example, if you have a butane chain and you have a OH on the end of it, it'd be butanol. So first let's look at the priority. The priority of how to name things is a much longer list, but for the ones that kind of concern us, we have the highest of priority is alcohol, and then under that you actually have alkenes and alkanes. Alkenes and alkynes are on the same level, but if there is an equal number of carbons, so say like you add up the different numbering and it's equal, then you actually would go with an alkene over an alkane. It takes priority over an alkane. But that's only if the carbons are, if the carbon numbering is equal. And then the last priority is an alkane. So how you name it is you find the longest chain with the most amount of OHs, and that's the chain you assign the name to. If an alcohol becomes a substituent, so for the priority, a carboxylic acid is above an alcohol. If there's a carboxylic acid on the chain, then you would actually change the alcohol from being the suffix of OL, and it actually becomes a prefix of hydroxy at the beginning of the name. So let's look at some examples. So right here for our first example, we have just a compound, and then so we're going to start numbering. So like I said, the priority, alcohol has top priority over an alkene, which is also on this carbon chain. So then you just start numbering from the alcohol. So you got 1, 2, 3, 4, 5, and 6. And you decide to number this chain because it has an OH, but it also has an alkene. You want to pick the chain that has the most amount of high priority, the high priority groups, if there is, if that's a possibility. So for this carbon chain, we have an OH on the second, so that would be an OH on the second. We have an alkene on the 5th carbon, and we have an ethyl group on the 3rd carbon. So you start off by naming 3 ethyl, and then it's 6 carbons, so it's going to be a hex group. And then so since alcohol takes priority, you actually would number it. So you name it 5 ene 2 all. And that would be the name of this carbon chain. So next we look at their physical properties of alcohols. First off, they're generally very highly soluble in water because of their capability to accept hydrogens and donate hydrogens because of their H bonding. Some parts that play into their solubility is their hydrophobic area. If their hydrophobic area is to increase, then their solubility will decrease. And if their H bonding possibility increases, then their solubility actually increases because it's more likely to donate and accept hydrogens. For the boiling point, they are relatively high, also again because of H bonding, so they can withstand higher temperatures relatively than other carbon chains. And they're also acidic because when they break off, if you have, for example here, we have a methyl group attached to an OH, and the OH gets a partial positive charge while the hydrogen gets a partial negative charge. And so that actually creates the OCH3 to have a negative charge on it, which makes it acidic, and then it breaks off a hydrogen with a positive charge. And those are some of the physical properties of alcohols. Next, we're going to look at the synthesis of alcohols, and there's a lot in this section, so I'm going to kind of break it down. The first way is if you take an alkane and you want to convert it to an alcohol, you have to convert the starting material to an alkene and then add water. So with this example here, say you have a butane and you want to change it to 2-butanol. Well, first you would, this is one way to do it. You would do a bromination in the presence of sunlight. And that would add on a bromine group on one of the secondary alkanes because it's a higher priority. And then you would take that bromination and you would cause it to, I'm gonna write the reactions in red. And then you would take this bromination and you want to do an elimination reaction. So I'm going to use KOH and heat to make it do a quick E2 reaction. So then that's the product you get from that, because it would go from the secondary, so E2. Yeah. That would be the Hoffman product, I think. Yeah, I'm pretty sure. And then, so you would take that alkene, like it says, so you convert the starting material to an alkene, which we did, and then all you have to do is add water. So I'm gonna add water in the way of, here, let me see if I have enough room. You're going to do HGOAC2 with NaBH4 and H2O. We'll add that OH. So then, now you see that once you have this, it'll add an OH on a higher priority group, but they both are the same, so it added on to either. And you end up getting this 2-butanol from this butane. And that's just one example of how to convert an alkane to an alcohol. Next, let's look at the synthesis of alcohols using a reducing agent. And a reducing agent is actually able to supply H- ions. So the three major reducing agents that we can use is H2 with a metal catalyst. We can also use lithium aluminum hydride with a H3O plus quenching reagent, and then we have sodium borohydride with an H3O plus quenching reagent as well. And so for the H2 reducing agent, we see that it can reduce C double bond C, so alkenes, alkynes, C double bond O, C double bond N, and C triple bond N. For the second reducing agent of lithium aluminum hydride, we have C double bond O, C double bond N, and C triple bond N as all the agents that it can reduce. So it can't reduce C double bond C or C triple bond C. That's the difference between these two. And then we looked at sodium borohydride, and that can reduce only aldehydes and ketones. And so when you're doing problems, that can get kind of messy because they'll try to throw you off by maybe throwing an ester in there, which looks like a ketone at first. But let's look at some examples, and I can show you how to use these three different reducing agents to synthesize alcohols. Okay, so let's look at some examples of synthesis using reducing agents. First, we're going to use, we're going to do the same exact compound for both of them, but in the first one we're going to do sodium borohydride, and we're going to look at how that reduces this compound. So first we notice that, we know that sodium borohydride can reduce aldehydes and ketones. And so if you look you see the ketone right here. It's a bad circle. And this is, at first glance, it kind of appears to be a ketone because you see this C double bond O, and it looks like it has just C's on both sides. But if you look closely, this is actually an ester group, and ester groups cannot undergo reduction, especially by sodium borohydride. So what happens is that this compound actually turns, so we have the cyclohexene, and that double bond O will get attacked, and this will actually turn into an O negative because this bond will come up, and then the quenching reagent goes in and adds a hydrogen, which makes it OH. And then for this part down here, it will actually not react at all. It'll stay the exact same, since this reducing agent cannot do anything to an ester, so it stays the same. Okay, so yeah, next let's look at that same compound, but with lithium aluminum hydride. So once again, we see that there is we know that this lithium aluminum hydride can reduce any C double bond O, C double bond N, or C triple bond N. So we see a C double bond O right here in the form of a ketone, and there's a C double bond O right here, and that's it because this is a C single bond O, which it can't do anything to that. So let's draw the product. So once again, that double bond O turns into an OH, and this double bond O also turns into an OH, but this is where it gets kind of tricky. So whenever this compound reacts with the lithium aluminum hydride, this, since it can't react, it actually cleaves off right here, and that part of the compound cleaves off on that C single bond O. And so your product, this entire part of the compound actually gets expelled, and the product would look like this, stopping right here with the C bonded to the alcohol group. So you can see the obvious difference between the two, since lithium aluminum hydride can react with C double bond O, it reacts with both of those, and then since sodium borohydride can only react with a ketone and aldehydes, it doesn't react with the ester down here, it only reacts with the ketone up here and makes a alcohol up there, or alcohol right there. And so those are some examples of how to use reducing agents. Next, for the synthesis of alcohols, we'll look at how to reduce the amount of carbons in a chain. So if you want to take your chain and make it smaller with less carbons, this is how you do it. You either have to use ozonolysis or hot KMnOH4, because both of these will actually cut the chain right in half. And for these reactions, you need an alkene, because ozonolysis will cut the chain right in half. Hot KMnOH4 will cut the chain right in half. And ozonolysis will produce aldehydes and ketones with the product after cutting the chain, and then hot KMnOH4 will produce carboxylic acids after it cuts the chain. So let's go in straight to some examples.